Have you ever watched a bat flit across the night sky and wondered, how on earth did they do that? Bats are the only mammals capable of true powered flight, a superpower that makes them seem almost otherworldly. But their origin story is one of the greatest and most fascinating mysteries in all of evolution. Today, we're diving deep into the shadows to uncover the truth of bat evolution. Imagine a world 66 million years ago. The dinosaurs have just vanished, leaving a planet of opportunity for the small mammals that survived. It was in this new world that a small four-legged creature began an evolutionary journey that would defy gravity itself. But here's the kicker. The fossil record for this transformation is incredibly sparse. It's like a book with the most important chapter ripped out. For decades, scientists had theories, but very little proof. They were stuck. The story goes from a ground-dwelling mammal to a master of the night sky. But how? Did they first learn to glide like a flying squirrel? Or did they develop echolocation first, navigating the dark before ever taking to the air? This flight first versus echolocation first debate has been at the heart of bat paleontology for years. It's a classic chicken and egg problem. To fly effectively in the dark, you need a way to see without light. But to evolve such a complex sonar system, maybe you need to be in the air first, where it's most useful. Which came first? For a long time, the oldest known bat fossils, like Icaronicterus*, which lived around 52 million years ago, were already fully formed bats. They had long, delicate wing bones and the specialized ear structures needed for echolocation. It was like finding a fully assembled airplane with no blueprints or early prototypes. These fossils told us what a bat was, but not how it became one. They were already perfect little flyers, suggesting the origin story was much, much older. The mystery just deepened. Where were the missing links? Where were the protobats? They named it Onychonicterus finni*, which means clawed bat. This creature lived about 52.5 million years ago, and it was the most primitive bat skeleton ever found. It was the missing link everyone had been searching for, and it held a surprising answer to the big debate. So, what made Onychonicterus* so special? Well, when scientists examined its skeleton, they found a fascinating mix of features. It had claws on all 5 of its fingers, not just the 1 or 2 that modern bats have. This suggests it was a powerful climber, scrambling up trees much like a squirrel or a lemur. Its limbs were also somewhere between a walking mammal's and a flying bat's. It had long fingers, a key requirement for wings, but its arm proportions weren't quite optimized for powered flight like modern bats. It could fly, but it probably wasn't as agile. It likely used a simpler, more fluttery flight, perhaps interspersed with gliding. But the most shocking discovery came from its skull. The cochlea, the part of the inner ear crucial for high-frequency hearing and echolocation, was underdeveloped. Onychonicterus* could hear, of course, but it lacked the sophisticated anatomy to navigate using sound alone. The verdict was in. Flight came first. This incredible fossil proved that our earliest bat ancestors learned to fly before they perfected the art of echolocation. It flipped the old debate on its head. This discovery painted a whole new picture of early bat evolution. Imagine this little creature, Onychonicterus*, climbing high into the trees of an ancient forest. It would launch itself into the air, fluttering and gliding from branch to branch, perhaps to snatch insects or escape predators. It was a creature of both the trees and the air. Since it couldn't echolocate, it likely hunted during the day or at dawn and dusk when there was still enough light to see. It was carving out a new niche, but it hadn't yet conquered the darkness. So, if flight came first, how and why did echolocation evolve? The evolution of flight opened up a whole new world of possibilities. The sky was an untapped resource, full of flying insects. But this new aerial world was also competitive. Birds had already been ruling the daytime skies for millions of years. To avoid competing with them, early bats needed a new strategy. The answer was the night. The nighttime sky offered a vast, open buffet of insects with far fewer predators and competitors. But to hunt in the dark, you need a new set of senses. This environmental pressure is likely what drove the evolution of echolocation. Bats that could produce high-pitched squeaks and interpret the returning echoes had a huge advantage. They could see in complete darkness, navigating complex environments and pinpointing tiny, fast-moving insects with incredible precision. The evolution from a simple call to a sophisticated biosonar system would have happened gradually. It might have started with basic sounds to avoid bumping into trees, and over millions of years, it became refined into the complex system we see today. Fossils like *Ichoronycterus*, which lived shortly after *Onychonycterus*, show us this next step. They had the full package: advanced wings for agile flight and the specialized ear bones for echolocation. They were the true masters of the night. This incredible 1-2 punch of evolution flight first, then echolocation allowed bats to diversify into the incredible array we see today. There are over 1,400 species of bats, making up about 20% of all mammal species. They live on every continent except Antarctica. Some are tiny, like the bumblebee bat, which weighs less than a penny. Others, like the giant golden-crowned flying fox, have wingspans of up to 5.5 feet. And they don't all eat insects. Over millions of years, they've adapted to eat fruit, nectar, fish, frogs, and yes, even blood, in the case of the 3 species of vampire bats. This incredible diversity is all thanks to that initial leap into the air and the subsequent conquest of the night. It all started with a small climbing mammal that dared to fly. But the story isn't over. Science is always moving forward, and new discoveries are constantly refining our understanding. Genetic studies are now adding another layer to the story. By comparing the DNA of different bat species and other mammals, scientists can build a family tree and estimate when different groups split off from each other. Some recent genetic analyses suggest that bats might be more closely related to a group that includes carnivores, like dogs and cats, and even pangolins, than to the primates and lemurs they were once grouped with. These genetic tools are powerful because they don't rely on the spotty fossil record. They can look back in time, tracing the molecular clues left in the code of life. While *Onychonycterus* gave us a physical snapshot of a moment in time, genetics helps us connect the dots and fill in even more of the gaps. The combination of fossil evidence and genetic data is giving us the clearest picture yet of how a small, ground-dwelling mammal transformed into the winged wonder of the night. The evolution of bats is a testament to the power of adaptation. It's a story of opportunity, innovation, and the relentless pressure of the natural world. From a humble tree climber to a master of flight and sound, the journey of the bat is one of the most dramatic transformations in the history of life. It reminds us that even the most fantastic abilities in the animal kingdom have an origin story, a step-by-step process of change over millions of years, even if some of those steps remain hidden in the shadows of deep time. So the next time you see a bat silhouetted against the moon, remember the incredible evolutionary saga that made it possible. Think of the brave little climber that first took to the air, and the generations that followed, refining their skills to become the true, undisputed rulers of the night. Thank you so much for joining me on this deep dive into the evolution of bats. If you found this as fascinating as I do, please hit that like button and consider subscribing to the channel for more explorations into the wonders of the natural world. Let us know in the comments what evolutionary mystery you'd like us to tackle next. Thanks for watching, and we'll see you in the next video.